Hi, welcome to me313, Mechanical Engineering Thermodynamics. The topic on this video is heating and cooling of air-water mixtures, and the section in the textbooks is 14.7. So here are the learning outcomes. At the end of this video, you'll understand qualitative relationships between humidification or dehumidification and then heating and cooling processes with respect to the psychrometric chart. You'll be able to apply the correct energy and mass balances to an HVAC situation. Remember, HVAC is heating, ventilation, and air conditioning. So this is more or less what we're talking about in this chapter. And then finally, you'll be able to solve for the inlet and outlet conditions of an HVAC system. We'll do this both using the psychrometric chart, and then we'll also do a solution using EES. So first, let's just go ahead and review some of the HVAC processes here. So here I've just got a sketch of the psychrometric chart from the textbook. And remember, down here on the x-axis, this is the temperature, often called the dry bulb temperature. I like to think of it just as the absolute temperature, the actual temperature of the air. And then over here on the y-axis, on the right-hand side, this is the humidity ratio, usually using the Greek symbol omega, which is going to be the mass of water per mass of air. So remember, the mass of the water divided by the mass of the air that's actually holding that water. All right, and so what's shown here in the diagram here are different processes: cooling and heating and humidification. So it kind of helps to remember what some of these other lines are. And so this curved line right over here is the limit of this psychrometric chart, and this is where the relative humidity is 100%. So essentially it's completely saturated. The air can't hold any more water than that. If you want to know where the limit of the minimum is, which would be 0%, well, that's when there would be no water in there at all. So that means omega would be 0. So this line down over here, the horizontal line, that would be where that is equal to 0%. So we go from 0% in this horizontal line, 100% to this curved line. And so more or less you're going to have some curves in here that look like this of various degrees of humidity. So maybe something right about there would be 50% humidity. Increases as I go up in that direction, and they never cross, but they're obviously not parallel. So let's look at a couple of these different processes. So for example, if we just look at humidifying means we're just adding water to it, which means we're just adding omega. That would be going upward. So then clearly humidifying was removing liquid water from it. We're going to be moving downward. And since the x-axis is the temperature, it's pretty obvious that going to the left is cooling and going to the right is heating. And so often we're going to go ahead and maybe do just one of those processes, or a combination, like maybe humidifying and heating, where we're going up and to the right. So we'll go ahead and look at this in a little bit more detail on this next slide. So again, let's go ahead and look at a couple different processes that might occur in an HVAC system. So first we'll go ahead and look at, for example, just heating. So imagine I've got some air coming in here. An air-water mixture, and this is a heating coil. So we're putting some heat into the system that way. And if you want to think about where this would occur on our psychrometric chart, let's again label our axis. This right down here is the dry bulb temperature, and this right over here is the humidity ratio. And if we are just heating it, so we're just doing some dry heat across here, we're not changing W. We're not making it go up or down, but we're increasing the temperature. So that means that we would have our inlet condition, we would be going just due to the right. That one's fairly straightforward. Let's go ahead and look at one with a little bit more details to it. So now let's go ahead and look at where I'm going to be humidifying air. So here I've got my airstream maybe going in this direction this way, and I'm putting in some steam, maybe some saturated steam at some temperature here, and I'm spraying it in here, coming in as steam to go ahead and increase the humidity. So if I want to look at what's going on here, let's just imagine, we'll just say this is our inlet condition. It doesn't really matter where we start. And what are we doing? Well, we know that we're adding water, so that means that we're going to be going upward. But the other thing is what we're doing is we're adding saturated steam. And so what this is going to be doing is also adding energy, which is going to be increasing the temperature. So we're probably going upward and to the right. So we're doing a heating and humidification process at the same time. Now, it would be in theory possible to be going up and to the left if for some reason the air here was incredibly hot, hotter than the saturated steam. That's really rarely happens. So really you're almost always going to be going to the right and going instead of going to the left. But you're always going upwards. That's one thing to remember. Because you're adding water, you're increasing the humidity ratio. All right, let's look at one last one, a little more complicated here. What we've got here is a dehumidification process with some condensation. So air is coming from the right, going in that direction there. It's coming through. We've got some coils here, and these are actually cooling coils. And so what we're doing is we're removing heat. It's coming out of the system in that direction. And what happens is the air cools down, and at some point condensation begins. So if we want to think about where this goes, let's just again pick an arbitrary point. We'll say we start right there. Initially, we're cooling it off. We're just going to be going straight across. And then at some point, the condensation happens, and we begin to dehumidify, and we go downward. And so we're going to end up at some point, too, right down there. So in general, we're going downward and to the left. But if you think about the processes, I move across there, I'm going straight across, and then in the second part, I'm going downward. I'm continuing to cool off as I remove energy from it with my condensate, and then you go downward in that direction. So there's kind of some just qualitative ways that this works. Now let's go ahead and look at our mass and energy balances that we would do for these kinds of systems. So first we'll go ahead and look at just our simple heating system. And so if I want to look across here, if I want to do the mass balance, well, if I do a mass balance on the air, I've got the mass flow rate of air coming in, so I'll call that MA1, and that's simply the mass flow rate of air coming out. Right? We're not destroying air, we're not making air, it's just going to be the same going in and out. And it's actually pretty simple. And so for these cases where I've just got one inlet and outlet, we'll just go ahead and call that the mass flow rate of air. We won't talk about it being inlet or outlet because they're all the same. Now let's go ahead and look at our mass balance over water. Well, now what we're going to have is we have the mass flow rate of air times the humidity ratio, which is going to be omega 1. That's going to be going in just the heating process. Remember, we're not changing it. It's going to be the same. So it just becomes MA omega 2. And what you realize there is that omega doesn't change. Omega 1 is equal to omega 2. We're just going horizontally across the line. So there the mass balance is fairly straightforward. If we look at the energy balance, we're doing heating. So again, we're adding Q. Q is coming in here. So what I have again is the mass flow rate of air. And now what I'm doing is multiplying this by the enthalpy, H1. And then the other thing that's going in is Q. So I'll go ahead and add my Q here. And that right there is going to end up being the mass flow rate of air times the enthalpy going out. So there's my energy balance. Those are two separate equations, a mass balance and an energy balance. Let's go ahead and look at those other processes we were looking at. We have this humidification process here. So again, if we look at our inlet on the left and our outlet going on the right, if I want to do my mass balance, what I've got again is the mass flow rate of air times its humidity ratio. And now the other thing that I'm adding, let's draw a little box around here, realize we're adding some water. So I'm going to go ahead and call that M sub W, which is going to be this water that's being sprayed in at some particular rate. And then what's coming out, mass flow rate of air times omega 2. So there's what my mass balance is. And the thing that I've added now is this water that's being sprayed in at some particular rate. If we look at the energy balance, well, mass flow rate of air times the enthalpy going in. And now we've got the enthalpy that's associated with this stream coming in. And that's going to be, well, we have the mass flow rate of water times its enthalpy. This is the enthalpy of that saturated steam that's coming in. Or it could be superheated steam. It's often somewhere around saturated or superheated. And that's going to become the mass flow rate of air times H2 coming out. Now, again, the conditions coming in, this value of H is usually going to be specified. And as I say, it's often Hg, which is just saturated steam at some particular high temperature. So you can go ahead and pull that value off of your saturation tables for pure water, because this is pure water that's coming in. It's not an air-water mixture coming into that pipe. Okay, so there's my energy balance of that. Let's go ahead and look at our last case that we looked at, which was this dehumidification process. Here we're coming in on the right and leaving on the left. And so let's go ahead and look at what our mass balance would be. Well, this comes pretty straightforward again. It's all mass flow rate of air times the humidity ratio coming in. And so let's look what's coming out. Well, we've got this box. We've got the water's dripping out. So that's coming out. So that's going to be the mass flow rate. Call it M sub C for the mass flow rate of condensate. And then, again, mass flow rate of air times omega 2, or the humidity ratio of 2. So I've got this mass flow rate of condensate value. Now, if we do our energy balance, again, what's going in, just the mass flow rate of air times the enthalpy. That right there, that is going in. And that's the only thing that's going into that little dashed box. Let's look at what's going out. Well, here we've got cooling. So in this case, Q is going out. So that's an out term. And so I'm going to go ahead and have the heat that's being removed, and again the mass flow rate times the enthalpy that's leaving. And then I also have to account for the fact that I've got water dripping out over here. So I've got my mass flow rate of condensate times its enthalpy. Often that's going to be H sub F. It's going to be a saturated liquid. So again, I can go ahead and pull that off of the saturation tables at whatever temperature that this is condensing out as. Again, I mentioned that this is cooling. This is often this Q out. This is often maybe some chilled ice water or something, and so we might find that separately for some mass flow rate of that ice water times C times some delta T that it has. So this water would be kind of heating up as it goes ahead and removes heat from the system, and that would be some sort of separate balance that we have, or it might just be specified at some particular rate. Okay, let's go ahead and look at an example. And so here's the example that I have. I've got air coming in from the left-hand side. It's coming in at 10 degrees Celsius and a relative humidity of 70%. I'm given a volumetric flow rate coming in. I've got some heating going on, so some Q that's going in. And then after it's heating, I'm adding some saturated vapor at 100 degrees, and I'm adding some water and some additional energy that's coming in with that. And now it's leaving at 20 degrees Celsius and 60 degrees. So let's go ahead and just write down what our relative mass and energy balance would be for that system there. I'll call the inlet is going to be conditions 1, and the outlet will be condition 2. So let's write our mass balance first. We're going to have mass flow rate of air, right? And it's going to end up being omega 1, which is the humidity ratio going in. And then we're adding some water, so I have this M sub W that's coming in, and that's going to end up being mass flow rate of air leaving times omega 2. So there's my mass balance. And now let's look at the energy balance. And the energy balance, mass flow rate of air times H1 is going in. The other thing I have, I'm heating it. So there's my Q value that's coming in. And then I'm also, right, we're also going in is that flow rate of water, mass flow rate of water times its enthalpy. It's saturated vapor at 100 degrees, so I'm going to call that H sub G. We'll look that value up just off of the saturation table. And then the only thing that's leaving is the mass flow rate of air times H2. So now what I have is my mass balance and my energy balance. So hopefully that's going to be enough to solve the problem. And let's look at what we know and don't know. Notice that we've got these two conditions given, a temperature and humidity both at the inlet and outlet. So that means we can find enthalpy values, we can find humidity ratio values, we can find volume, we can find anything that we need, any sort of intensive variable that we need. We need an extensive variable, which is the mass flow rate of air, but there's my extensive given, which is the volumetric flow rate at the inlet at 35. So that's going to go ahead and let me get the mass flow rate of air. So that means I can go ahead and solve these two equations and get all of my values, because I have two equations and I have two unknowns. I don't know what Q dot is, and I don't know what the mass flow rate of water is coming in, that M sub W. But just two unknowns, two equations, we can go ahead and solve that. So, oops. Let me go back here. All right, so let's go ahead and first we can go ahead and find or just directly find our mass flow rate of air. And that right over there is going to be the volume flow rate that's given at the inlet over times the volume going in. Again, this is an intensive variable I can get off of the chart. So let's go ahead and look where I am. I'm at 10 degrees and 70%. So let's go over and look at our psychrometric chart. 10 degrees, so I'm down here. Here's my 10 degrees, and I'm at 70%. So I'm going to go up to the 70% line, which is this point right there. So there's where my inlet condition is. And we can go ahead and read all of our values off of that. And so, for example, one I need to go ahead and find is the volume. Now, volume's not particularly easy, just so you know. It's these sort of slanted down and to the right values on this diagram. They're in the pink here. That's 0.82. So I'm really at about 0.81. So my volume, specific volume, is about 0.81. So we'll go ahead and use that value there. So what I have is 35, and that's cubic meters per minute. So I'll go ahead and express that per second. So 35 over 60, and we'll do that over 0.81, which is going to be my specific volume that I got off the chart. And so that's about 0.72, and that's going to end up being kilograms of dry air per second, because I did per second because I divided there by 60. So now I've got my mass flow rate of air, my extensive value. So now the rest of these is just using these two equations. So let's go ahead and solve for our mass flow rate of water first, because that appears in the first equation where I have two unknowns, both Q and MW, in the second one. So we'll solve the first equation first. that I've listed up there. So I've got my 0.72, which is the mass flow rate of air. And now what we need to do is find what omega 1 is. So I'll come over to my psychrometric chart again. And so I've got this point. I look straight across over here to go ahead and find out what that value is. And if I look over, I'm coming over here. Again, it's always kind of hard to tell. I'm just a little above 5 probably. So I'm going to go ahead and do 5.3. So that's going to be 5.3. And remember, that's grams per kilogram. So it's gram of water per kilogram of dry air. And then MW, which is what I'm trying to solve for. And that's going to be 0.72. And now I've got to look at my outlet conditions. So my outlet conditions are 20 degrees and 60%. So let's look at that. Come over again to my psychrometric chart. Now I'm at 20. And I'm going up to 60. And that's going to be right there. Okay, so now that's where my point is. So now again, if I want to find W, I'm going to look straight across at that value. And looking across, oh, it's a little above, not quite to 9. I'm going to do 8.7 on that one. So this will be 8.7. 8.7. And now I can go ahead and solve for what MW is. Oops, excuse me. Solve for what MW is. And that value is about, oh, if you do that math, that's 2.45. And that's going to end up being grams per second, so 0.00245 kilograms per second. All right, now we know MW, so now I can use that second equation, my energy balance equation, to solve for Q. So let's go ahead and 0.72, my mass flow rate of air. And now what we need to do is find our enthalpy. So enthalpy of the inlet, so let's go ahead and look at that. Go back to our psychrometric. Here's this point, and no enthalpy values. That's these over here on this diagonal line, where this is 20. So if I look over, I'm up at about, oh, I'd say 23. I realize it's kind of hard reading off these charts, but I'm going to say that that's about 23, which is the enthalpy going in. And then Q dot, which is what I'm trying to solve for. And now I've got my mass flow rate of water that I just found, 2.45 grams. Do this in per kilogram, 0.0245. And then I need my enthalpy. I'm told it's saturated vapor at 100 degrees. That's my H of G value at 100 degrees. I'll look that up off the table, and that's 2676. That comes off the steam tables. And that right there is equal to what's going out, which is 0.72 mass flow rate of air. And now I've got my outlet enthalpy. So let's go ahead and look at that last value. Outlet enthalpy on the psychrometric chart. Looking up there, I'm at about, oh, let's say 42. So 42. And now I can go ahead and solve for Q. And if I do that, I get a value of Q that is about 7.1, and the units on that are kilowatts or kilojoules per second. All right, so that's how we do it by hand with the psychrometric chart. Let's go ahead and look at another problem. This time we'll go ahead and solve it with EES. But first, let's kind of discuss what's called adiabatic mixing. We'll just kind of complicate things a little more. What we've got is we're going to have two streams coming in here that we're mixing together, and then have an outlet stream there. So we'll go ahead and what do we do there? Well, the thing is, if we have those kind of conditions, we're going to have an additional mass balance, because now our air mass balance is the mass flow rate of air at 1 plus 2 going into 3. So we've got an air mass balance and the water mass balance. Now the water mass balance is the same one that we saw before, but again, now we don't have a constant mass flow rate of air. We've got an A1, an A2, and an A3. So they're going to be coupled through that air balance. And then if we look at our energy balance, again, we're going to account for the different mass flow rates of air coming in at each point. Okay, so just a little bit more of a complication when we are also mixing streams, but won't be too bad. Okay, let's go ahead and look at an example problem. So here's the example problem. We're going to go ahead and we'll solve this one in EES just to change things up. So here what I have is I've got these two streams coming in. I've got one coming in at the top, which is a warm stream. I'm told what its humidity ratio, or sorry, not its humidity ratio, it's relative humidity at 80% and 28 degrees. So it's apparently pretty hot. So maybe it's like I'm bringing in some hot, humid air out of Florida at a particular volume flow rate. And what I want to do is I want to go ahead and mix these down together, and I want an outlet condition that is going to be 50% humidity and 22. I'm going to do that by doing some cold air. This cold air is going to come in at 10 degrees Celsius and relatively dry at 10%. And then it's going to go ahead and I want an outlet of those conditions, which means I'm also going to need, there's nothing that says that temperature is going to be exactly 22 and 50% humidity. And so what I'm going to do is I'm going to have some heating. In fact, I think I have a little picture there. I've got a little heating coil over there. And I'm going to say it's heating for now. If I solve a negative value, it'll just be cooling to go ahead and draw it down to those conditions. So maybe we'll put a little double arrow. We don't know which direction, if it's going to be heating or cooling that we need. Okay, but we know that we need this content of water at that particular temperature. So there's the problem that we want to go ahead and solve. So let's go ahead and this time what we'll do is we're going to solve this in the ES, but let's just go ahead and do our energy balance box that we do over here. And remember this as I move over to EES, what I have. I've got my two inlet conditions right over there, which is going to go ahead and tell me what all my intensive properties are. I have one extensive value, which is that volume flow rate there that's coming in of the warm air. And so that's going to be left to what's found at the outlet. All right, so let's move over to EES and go ahead and look at this problem. Okay, so here I have it in EES, and one of the things that I'll first mention, and you'll see this, is that when we use these functions in EES, we also have to specify the pressure. The psychrometric chart, remember, is at atmospheric pressure. It turns out that you can go ahead and do other pressures in EES, but we'll go ahead and use atmospheric. So we're doing this in SI units. We can give that value at 101, and that will be in kilopascals. So let's go look at our, first of all, specify our outside air, the air that we're bringing in. This is that top stream. We were told its relative humidity was 80%. In EES, it's going to be an R value of 0.8. And then our temperature was 28 degrees. And from that, we were also told that we were bringing in air that was at 0.2. And that was cubic meters per second. And so I can go ahead and find the mass flow rate coming in. This is the mass flow rate of air. I just called it M here, but the mass flow rate of air, 0.2 over, and then I've got, just to use this volume function, where I've got air water is the material that I'm using in the ES. I give it three parameters now, the pressure, and then R and T. And since I'm always going to be doing atmospheric, I define that as P naught, so I can just always say P equals P naught, and then R is my relative humidity. That's a number between 0 and 1, so don't do 80, you do 0.8. And then the temperature, which is degrees Celsius. And then here's my coolant air, two conditions, a relative humidity at 10% and a temperature of 10 degrees, so it's pretty straightforward. And we were told what the outlet is. We wanted it at 22 and a relative humidity of 50%, so an R value of 0.5, right? So those are all just givens. So now let's look at these next three. These are my three energy balance equations, or sorry, my three balance equations, energy and mass balance. So simply my mass balance, which is M1 plus M2 is M3. So those are all mass flow rates of air. I'm just calling them M here. And then my energy balance, M times H going in, M times H of the other one going in is M times H. So fairly straightforward on that. And then my water mass balance, you should recognize. M times, I'm using W, that's the omega parameters. I just like W instead of spelling out omega. M1 omega 1, M2 omega 2 is M3 omega 3. So hopefully those seem fairly straightforward. Since we have two conditions at the inlet, the outlet, and then also at both inlets and the outlet, we can go ahead and find any properties we want. So now these next series of 5 equations are just whatever properties I need. So it's effectively reading off the psychrometric chart and having EES do it for me. HumRat is the humidity ratio. That's going to give me omega values, which is my W. Enthalpy is the same, but again, remember to use the material called air water. That's air H2O. It's one thing. One word, and it's going to end up giving you the properties of that mixture. And then the humidity ratio of the other stream coming in, and the humidity ratio going out. And so I can go ahead and I could find volumes and anything else that I needed on here. I didn't need anything else. And then the final part was to find the volume of the cooling air. So then that was going to end up be whatever my volume is of stream 2, which I can find. V2 is just using the volume because I've already found all my outlet all my cooling air conditions there, and that's going to go into me what the volume of the cooling air needs to be. So assuming I have all that right, I should be able to go ahead and solve this. And now if I go ahead and look at my solutions, let's go ahead and first we'll go ahead and look at our solution array table. If I expand that, so remember stream 1 was the warm stream, stream 2 was the coolant stream. It's my 80%, 10%. And then this is right over here is what's getting mixed together. And then coming down to my solution, the only one that really matters is the volume of cooling air. So I need to add air at a rate of 0.267 cubic meters per second. and that's going to give me the desired outlet that I want. So hopefully that seems fairly straightforward. So again, just kind of going back to ES, I think kind of laying it out this way with your balance equations one point, and then just all the intensive properties you want elucidates very quickly on how to arrive at the correct solution. Okay, and so I think that wraps it up.